This begins a series of screencasts on dynamic programming, a problem-solving method for addressing optimization problems. The images for this series will be from dynamic locations on the coastlines of Hawaii. This particular image is South Point, the southernmost point of the United States, and of course of the Big Island of Hawaii, during a heavy surf. A very dynamic location. And to give you a sense of scale, those things in the background on the plateau are automobiles. So far in this course, we've studied a number of algorithms, including algorithms for the dictionary, ADT, for sorting items, for searching for items in dictionaries, and there will be other algorithms to come, for example, to operate on graphs. For these well-studied algorithms, quality open source implementations exist. Often you don't need to implement them. You can go find, for example, a good quicksort and quickly adopt it to your data. But we're also studying problem-solving methods that guide the design of algorithms for specific problems. These are cases where there isn't necessarily an algorithm specific to your problem. You're going to have to write it yourself, but there's essentially design patterns for different ways of approaching problems. So what you need to do is to understand the characteristics of your problem, match the characteristics of your problem to these algorithmic design patterns, and then use the design patterns and associated strategies to design a custom algorithm. So dynamic programming is an example of such a problem-solving method that has design patterns with it. Other examples would include the incremental brute force kind of algorithms like the insertion sort, divide and conquer like the merge sort, where you divide things up into subproblems that can be solved separately, and dynamic programming, today's topic, and also greedy algorithms and other methods to come. Some of these, including dynamic programming and greedy algorithms and linear programming, solve optimization problems. These are problems where you are trying to you have a set of alternative solutions, approaches or solutions, and you're trying to find the best one under some metric. The metric could be something you want to minimize, such as cost, or maximize, such as revenue. So dynamic programming is one of several methods we're going to examine for optimization problems. Now, dynamic programming has something in common with divide and conquer. You take a big problem, let's say big P, and then you break it up into subproblems, maybe P1 and P4. And then perhaps you continue to break these up into subproblems until you hit some bottom problems. But dynamic programming does not apply when these subproblems are all different. Like in merge sort, where you break up the input data into separate sort problems. Solving one of those separate sort problems does not help you solve the other one. Dynamic programming applies when you see patterns like this. So I've just sort of made up an example here, but suppose here we got to solve problem PA, B, and PC to solve P1. In P2, we've also got to solve B and C. And over here in P4, we've also got to solve A and B. So a strictly recursive solution would keep solving these things repeatedly, wasting work. And so what we want to do in dynamic programming is somehow capture these solutions and then reuse them when we encounter the problems again. So let's look at this in a detailed example. Our example will be called the cut rod problem, and this is looking down into Waipio Valley. Okay, the rod cutting problem. Let's suppose you're running a hardware store and you can get really long steel rods, and your customers want pieces of different lengths already cut up. So you're going to cut them up, put them in bins, and sell them. And you can get different prices for different lengths, depending on not only on the amount of steel in them, but just how popular that length is. So you want to take the rods that you get and cut them up into pieces to maximize how much money you get. So you're given a table here, the length of a piece and what you can charge for it. And you're going to be given a rod of length n. For example, say if n is 8, you might ask, how do I cut it up to maximize my revenue? First thing we need to notice here is if we have a rod, which I'll just represent as a line, and let's say we're going to be able to cut it in 1 centimeter increments. Our choices are to cut at any of these locations here. So for each of these locations, we have the choice to cut or not to cut at each location. If this rod is of length n, then there are n minus 1 cuts in between the lengths. So if at each of these n minus 1 locations you can choose to cut or not to cut, you're going to get 2 to the n minus 1 possible solutions here. So checking all possible solutions is not really viable. Let's set this aside and look now at a particular example. Let's say we have a rod of length 4. How many different ways can we cut it up? And we got to remember that one option is to not cut it at all. Here's a rod of length 4. If we don't cut it at all, we look up in the table. This is going to give us a value of 9. Then we can choose to cut it into a piece of 1 and a piece of 3. So we look up 1, we get 1, 4, and 3, we get 8, 4. 1 and 8 also gives us a value of 9. Or we can cut it into 2 and 2. Look that up, we get 5 and 5, so we get a value of 10. That looks better. And we could also cut it the other way, which is the 8 and 1, but the prices are going to be the same, so I won't draw that. But then we need to consider, well, we might further subdivide these things. So we might chop off, for example, 2 pieces of 1 and 1 piece of 2. And so we get 1, 1, and 5, checking the chart, which gives us a total of 7. And of course, cutting at 1, 5, and 1 would give us the same, and 5, 1, and 1 would give us the same. And then the last option is cutting it into 4 pieces of 1, which would only give us $4 or whatever the currency is that we're working with. So we can see here that the best solution for this particular example is to divide this rod of length 4 into 2 rods of length 2. We're going to get the most money for it. Before we go on, we need to note an important property of this problem called optimal substructure. And this is that, suppose you have a rod of some length, and you determine that the optimal solution for this rod involves a cut here. So this is the optimal solution of this rod of length n. It must be the case that the optimal solution to the original problem up here incorporates optimal solutions to the subproblems here, which can be solved independently. You can prove this by contradiction. Suppose that this were the optimal solution, this S with this cut here, but it incorporated a non-optimal subproblem, S1. You could find the optimal solution to the subproblem, S0 or SO, and substitute it for S1, and then that would increase your revenue at this level, contradicting the assumption that this was an optimal solution. So this is called a cut and paste proof by contradiction, where you prove that something must be optimal because if it weren't, you could cut out the non-optimal one, paste in the optimal one, and then contradict your assumption that the overall solution was optimal. So what this means is that when you solve a problem of some larger size, you can just incorporate the optimal solution to the problem of the smaller size without having to resolve it. So if you can arrange to solve your problem in the order from small size to large, like in this table, we're going to solve for size 1 and then size 2 and then size 3 and so on, then you don't have to go back and redo the solutions for the smaller sizes. So let's run this example quickly. Size 1, of course, the revenue we have up here is 1 and there are no cuts. Size 2, we look up here and the revenue is 5, and we can look back in our table here and say if we cut it into 2 ones we get 2. So we're going to leave it at 5 with no cuts. Problem of size 3, if we leave it at size 3 we get an 8. If we split it into a 2 and a 1 we get 6. So that's no good, so let's stick with the 8. Size 4, look up in the table for that size, we get a 9. But if we split it into 3 and 1 we also get a 9. If we split it into a 2 and 2 we also get a 5. That's 10. That's good, so let's cut it at 2 and 2. Now the problem of size 5, okay, again we look up the table for that size because we haven't solved that before, so that gives us a 10. But let's compare that. Now here's the crucial thing. We don't look in the table here up here for 4 and 1. We look in the table here. Because if we looked up here we'd get 9 and 1, which is 10. But when we look up here we get 10 and 1, which is 11. So this is giving us the optimal solution to the subproblem, not just the size of the whole rod that's not broken down. So that would give us an 11, but we keep going here. Looking at this table, 3 and 2, that's a 8 and a 5. That ends up giving us 13. and that's with a cut at 2 and 3. 6, keep going. We can get a 17, or we can get a 13 and a 1, which is 14, or a 10 and a 2, which is 15, or 2 3s, which is 16. So the 17 will look good here. 7, we can get a 17 directly without cutting it, or we can get a 17 and a 1, which is an 18, or a 13 and a 5, which is also an 18. And it turns out that 18 is the best we can do. So we'll do it at 1 and 6. And then an 8, we can get a 20 directly. 7 and 1 will give us 19. 6 and 2 will give us 22. 5 and 3 will give us 21. It turns out the 22 is the best one. And so on. So the important thing is, although we look up the price for the uncut size in this table, we look up all the other subproblems in this table here, because some of these may be bigger numbers. Like, for example, the 4 was a 10 here, but it's only a 9 here. So that's going to be the gist of the dynamic programming solution to things, which is build up a table of the optimal solution to the subproblems, and the optimal substructure property lets us take those solutions, and we're guaranteed that they will be part of the overall solution, so we can just incorporate them and not worry about whether some other combination would be better. The thing we need to do is to quantify the value of the optimal solution. If we can write an equation, an expression for it that tells us something about the structure of the problem and tells us how to compute it. So for this problem, the optimal value for a rod of length n is going to be the maximum of all the possible ways of cutting it up. We can just stick with a rod of length n, or we can chop off a piece of size 1 and get the value of that, r sub 1, plus the value of whatever the solution is to a piece of n minus 1, and this may involve more cutting. That'll be the recursive portion. Or we can pick off r sub 2 plus r sub n minus 2, dot, 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 and eventually this will lead up to r n minus 1 plus r sub 1. So these are all the possible ways of cutting the thing in half. And so if we check no cut, or all the possible ways you can cut it in half, and then we get the recursive solution to those two halves, and find the maximum, we're guaranteed to get the optimal solution to the whole thing. But let's be a little bit smarter about this. There's redundancy in here. R sub 1 plus r sub n minus 1 is the same as r sub n minus 1 plus r sub 1. There's a symmetry in there. Also, we can simplify things by rather than having two subproblems, we can simplify things to say, let's just chop off a piece of size 1, look up directly its value, and then recursively solve the n minus 1. Chop off a piece of size 2, recursively solve the n minus 2. So we only have to have one subproblem rather than two, because we know that any solution will have either a piece of size 1 or a piece of size 2 or a piece of size 3, dot, 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 a piece of size n. So you don't have to have double recursion. We can do it with single recursion. So we write the formula out this way to reflect that. It'll be the max across the value of whatever size piece we cut off, piece of I, where I is going to go from 1 to n, plus, here's the recursive part, the value of the part remaining, r of n minus I. So this tells us what the recursive structure of the problem is, and we can now use it to build our solution to the problem. And note that we don't know in advance what I will be, what size of piece we should cut off, but we know that one of them must be right. So we'll check all of them. So let's use this analysis to show how we can actually solve the cut rod problem. And here we are on the Kau coast of the Big Island, which is a location reachable by the Helena Pali Trail, very remote, looking towards Pu'ukapu'ukapu. Sounds pretty forbidding. So let's transition to the web notes here to save some writing time. Here's the equation that we just came up with, and this maps directly to a recursive top-down solution, where first of all, if the rod is of length 0, we return 0, then we set the cost, or revenue, sorry, to a negative infinity, and then we're going to iterate over all the I being the possible first piece you cut off, and find the maximum of all those I's of what you get for cutting that piece off, plus the recursive solution for the remaining piece. So each iteration through the loop, we're going to ask, is the new solution cutting off a piece of length I plus the remaining solution bigger than what we had before? And so that implements this max here of the piece we cut off and the recursive solution for the subproblem. Okay, so that works, but how efficient is it? Well, a cut rod called on, for example, a problem of size 4 will cut off a piece of 1, and then it'll recurse here on a problem of size 3, and then I will be incremented, and then this on the next call will be of size 2, and then I will be incremented in the next call. This will be of size 1. But what happened during that first call to size 3? Well, cut rod of size 3 is going to cut off a piece of initially of size 1 and call recursively on size 2, and then eventually of size 1, but the call to size 2 is going to do it at size 1. And as you can see now, all of these calls in the tree are redundant. It's wasted work because these are all zeros, ones, and twos, and they've all been already computed as part of doing this work here. So that's the problem with basic recursive problem solving that we're trying to solve with dynamic programming. And the basic strategy is just to remember all these solutions and simply look them up when you encounter the problem again. But there's two ways to do that. Before we go on to them, I'll just note in passing that if we take the recurrence relation for this recursive solution and then solve it using substitution, we will get that t of n is exponential. One approach is to take the recursive algorithm and just add what's called memoizing to it. Memoizing is where you store results as you compute them, and then you look them up later on to see if you've already stored them. The entry procedure, memoize cut rod, is basically just a setup. You have an array of the revenue for each size, and you initialize them all to the smallest possible value. And then memoize cut rod, aux is going to do the actual work. Now this is actually the previous recursive cut rod modified. The part that was there before is this part here and this part here. If the problem size is 0, you're going to return 0. Otherwise, set to initial small value, check all the possible pieces you cut off, get the max of the price of cutting off that piece and the recursive solution. But the part that is added is the first thing you do is to see, have we already solved it before? And of course, since we have initialized things to negative infinity, any value greater than 0 is a previous solution, so we just return it and we save all that work. And the other part that's new is after we've computed the optimal value for this subproblem, we store it right here. Now, a runtime analysis of this, you can see that we've got a loop from 1 to n here, and so you can see how these recursive calls unroll. It's going to be an arithmetic series. These calls here are going to be n minus I, so it's going to be n minus 1, n minus 2, down to size 1. So it's going to be the sum of an arithmetic series, and that will give us n squared complexity for doing this. Now this has the advantage that it will not solve problems that aren't needed because it works top down. The recursion will do a recursive call only when you need to solve a subproblem, and in some dynamic programming problems that's a significant advantage. But it has a disadvantage of the overhead of recursion. You're setting up all these recursive calls on the runtime stack. So a bottom-up solution is usually more efficient when you have to solve all the subproblems or most of them. So here's an example of the bottom-up strategy with the cut rod problem. Basically, we have to have some notion of size. Whatever problem we're solving, we have to define size, which is a sense of what problems have to be solved first before other problems because they're subproblems. And then we have to solve the smaller ones first. And of course, with cut rod, the natural size is simply the length of the rod. Solve it for a rod of length 1, then solve a rod of length 2. We actually start with 0. So we have this array of the optimal revenue for the rods of each length. We set the 0, 1 to 0, and then we're going to work our way up. We're going to solve it for a rod of length 1 and work our way up to n. And so that guarantees, since our recursive call here is going to be rj minus I, and we're running I from 1 to j, we're always doing recursive calls on problems that are smaller than the one we're working on now. And that's important because you want to make sure that the order in which you do things You don't try to reference the solution to a subproblem before it's been computed. So solving problems from size 1 to n, set their initial solution to the worst possible, and then again iterate through the possible pieces you can cut off first, and then the subproblems, these of which will all have always already been solved. As before, record the solution for each size before you return the solution to the one that you're working on. Now, runtime analysis. Here again we have a loop j equal 1 to n, I equal 1 to j. That should be a very familiar pattern to you, and these are going to be just lookups because we have arranged for this piece here not to require any recursive call. It's just a table lookup. So of course, two nested loops, one running the n, one running up to the other one, is another arithmetic series which turns out to be order of n squared that we're familiar with. Of course, so far what we've done is just we've computed the revenue, the value of the optimal solution, but we haven't recorded how we got there. And of course we want to output that as well. So the simple extension is to add a second array for the solution for each size. And remember, since we do it, we have a simplified approach where we chop off a piece of a certain size and then solve it recursively. We just have to store one number for a given size. For example, a rod of size of length 8. We just have to restore the number which is the best size to cut the first piece off. And then the how to solve the two pieces that result will be recursively looked up in the table under the smaller indices. So we just take the same procedure we had before, but now we just elaborate this internal piece of code here to have this test here to say if we've got an improvement, not only do we record that improvement, but we also record right here the I at which we found the improved revenue. And so when you exit this loop, this S array will have recorded the best cut to make, and so you return both of them. So here's examples of the tables constructed for the problem we worked on before. Suppose we call the extended cut rod with 8, and it'll construct this table R and this table S. And what it says is, you look into the table for the rod size that you're working with, 8, and it says you can get $22 if you cut it at 2. And then you have to say, okay, well, now I've done that. I got a rod of length 2 and I got a rod of length 6. What do I do with them? Do I cut them? You look under the 2. No, you keep it the same size for the 5. You look under the 6, and no, you don't cut that. But there may have been cases where, yes, you do cut it. So we need a way to print the solution out. So this is print cut rod solution, which does the whole thing. Given it a table of prices and the length of the rod, it will call the recursive cut rod procedure that fills the tables or returns them, and then it goes into the table to print the entry for your size n. For example, if n was 8, it would go into the table here and print out 2. And then it does n is n minus whatever that entry is, so n minus 8 is 6, and it would go in the table for 6, and it would print out 6. And then 6 minus 6 is 0, so then this loop would exit, and that's what you would get. Cut a piece of 2 and a piece of 6. Well, that concludes our introduction to dynamic programming, just an example. Now we're going to go into more detail in the next screencast. And so we'll leave you at Keauhou, which is a camping location on the South Sea coast of Hawaii Volcano National Park.